So here's the calibration of the thermometers, and I have them both in a 250 ml beaker with 150 mils of water. And let's get close here. See that 21, they both seem to be about 21.5. So that's nice. So they show that they're pretty much identical. So we're going to assume that there is no uncertainty between the thermometers, and I'm just going to use one or the other for all of the experiments. All right, so we're going to find the heat capacity of the calorimeter by mixing room temperature water with heated water. And we're going to find that instead of the temperature evening out, since it's 50 mils and 50 mils, instead of being right in the center of those two temperatures, it's going to be off. And that's because some of the heat is going to go into here, into the calorimeter, and we need to know that for all of our other reactions, which are also going to be heating up. So this is how we find the heat capacity. We're going to take the room temperature water, 50 mils, goes in here. Oops. And then we're going to put the thermometer in here, see what the temperature is, so that's set. Then we're going to take 50 mils of water and put it into this beaker. And then the beaker goes onto this hot plate. I don't know if you can see that. Yeah, there we go. And we're going to put the other thermometer in here. And it doesn't have to be exactly 40 degrees. It can be anything you want. If it gets too high, though, let's say it gets to 80 or 90, it would still work. It's just this would be so hot it'd be hard to hold on to. So I'm going to let it go until it gets to about 40. And when it does, when I shut the heat off and I move this out, we have probably about 30-40 seconds before the temperature starts to drop noticeably. So we're all set to transfer it over here. We don't have to rush or anything like that. Okay, so it's been heating for a little bit, and it was at 40. It's getting a little bit hotter as I'm talking, but that's okay. I'm going to go over there and find out what the temperature is. I'm going to call that off, and then I'll pour it in here, and then we'll come over. I'm going to take the camera and then look at the temperature on here for the mixing. To mix it, we're going to use this little stirrer. So let me get that in here. So we're all set to go. Move this over. Okay, so it says, oh, it's at 46. So 46. Put this in. Get this in, put in the thermometer. And we're going to just mix it up a little bit, without breaking the thermometer, hopefully. And it usually settles in pretty fast. I'm just going to call it off here. Let's see, it is at, we are at 32.8. 32.8. Okay, things got a little out of hand there for the heat capacity experiment. That is, I couldn't call off everything at once. So here's all of the data. The temperature of the calorimeter in the cool water, that's 21.5 degrees Celsius. The temperature of the warm water is 46 degrees Celsius. And then that says the temperature of the mix at T equals 0. What all this means is the final temperature. Once we've mixed it up, what happens? So that what they're doing here for this lab is, if you were to graph out this the temperature change, you would extrapolate back to the T is equal to 0, but this happens so quickly, and then the temperature holds so steady that we don't have to worry about that. So when you see that mix at T equals 0, that just means the final temperature of the mixture. So that is 32.8 degrees Celsius. So this is the first acid-base reaction that we're going to do. It's going to produce its own heat, so the temperature will go up. That's why we don't have to heat these. Here's the 3 molar hydrochloric acid and the 3 molar sodium hydroxide, 50 mils of each, and they are at 21.5 degrees Celsius. We're going to mix them together. The acid goes in first, then the base, and the temperature is going to go up. We're not going to graph the data. I'm just going to show you the starting point, starting temperature, and the final temperature for these next 4 reactions. So what I found is that the graphing, going from room temperature up to the final temperature is a matter of seconds. They say to show the temperature every 10 seconds, but by the time you get it to, say, 20 seconds, it's all set to go. So we're just going to worry about finding the final temperature. So what I'm going to do is add in the acid here, and then I'm going to switch the view so that you can see the thermometer in here as I add in the base, and then you'll watch it rise up. Okay, so what we need here, here's our HCl. They say to put the acid in. I have the stir bar or stir rod in there. Okay. And then this sodium hydroxide is going to go in next, but I'm going to switch the view and you'll be able to just see the thermometer and watch the temperature rise. Okay, so we're going to put in the sodium hydroxide now. Oh, it's going to be a little tricky. Get this. And you in here. Fill this up. Without breaking the thermometer. Doesn't sound like they're colliding at all. You can see it doesn't take long for it to reach its highest point. Turn it a little bit. And I would say, yeah, essentially at 40. When you look down, this is a little bit above, it makes it look a little higher, but looking straight at it, it's 40. And here are the results for the sodium hydroxide hydrochloric acid reaction. Before mixing, they were at 21.5 degrees Celsius. And then when we mixed the solutions together, we ended up with 40.0 degrees Celsius. So here's the acetic acid and the sodium hydroxide reaction. So the 50 mils of 3 molar acetic acid are in here. And I'm going to add in the 50 mils of the 3 molar sodium hydroxide and see what happens. There. Oops. Looks like it's settling in. Harder to tell. So it is 38.5. 38.5. The results for the sodium hydroxide acetic acid reaction. We start at 21.5 degrees Celsius and the temperature rose to 38.5 degrees Celsius. And here's the last reaction. It's the 50 mils of 3 molar acetic acid in here, and then this is the 50 mils of 3 molar ammonia, and I can attest to this being ammonia. I can smell it from here. Pretty concentrated stuff. All right, so we're going to do the reaction again. Now this is we had a strong acid and a strong base at first, and then we went up to 40 degrees Celsius. Then we had a weak acid and a strong base, and it was a little bit lower in temperature. And then this is a weak acid and a weak base, so we should expect this to be the smallest temperature change. But let's find out. Oh, definitely ammonia. What do we got here? Yeah. So 1, 2. So 32. We'll say 32.5. Let me check that again. 31, 2. Yeah, 32.5. And here are the results for the ammonia acetic acid reaction. Okay, so we have this last sheet. I just wanted to give an example of how this works. these numbers here are not your numbers. I just found this in one of my lab books. I did this experiment out a couple of summers ago. Anyway, but you'll have your numbers that you'll put in here. They'll all be negative because they're all exothermic. And then the second part, it's Hess's law. We're going to take these and we're going to manipulate them and then add them up to get our heat of reaction for this reaction. Well, if you look at, it's a little tricky to tell, but all you have to do is flip the second reaction around, reverse that, and that's going to change this number from negative to positive. Everything else is the same. So then you just add them up, and that will be your value, your experimental value. So these numbers will be different. When you calculate them out, you're going to have some different numbers here, so this value will be different. But down here, this will be the same for everyone. These are the numbers from the table in our textbook. And when you put them in here, instead of solving by Hess's law, we're doing it in this way, based off of the heats of formation of these components. And we end up with this. So this is the theoretical value. This is what it should be. Here's what I got for my numbers a few summers ago. And yours may be different still from that. Most likely it won't be the same. But that's how it's set up. So just to give you an idea of how to do this last page.